started, let me make a very brief recap. We are studying the stability of rock and armor units, and it is a topic that you already studied with. I think you already discussed it with Professor Archetti. On the other hand, today I want to look at the physical mechanism that govern the process of stability, instability of these units. I make reference to both groins and breakwaters. Of course, our main focus is groins because we don't discuss breakwater in detail. On the other hand, I want to discuss in detail the physical process. You know that these design problems of harbor engineering are often dealt with empirical formulas. And I think, for instance, for this topic of stability of armor units, you already discussed with Professor Archetti, but if not, it's not a problem because we will make a recap. I think you already discussed the Hudson formula. The Hudson formula, as we will see, it's very useful indeed because it's a simple to apply empirical relationship that tells you whether the units that we put over a breakwater, rock or concrete armor units, tells you if they are stable. Fine. On the other hand, what I want to do is to try to gain with you today an improved knowledge of the physical process, because the empirical formulas have the disadvantage that they don't lead you to gain an intuitive understanding of what's going on. While I am firmly convinced that a good design must be supported by this improved and refined understanding of what's going on. And therefore, this is why I want to discuss with you the physical process. So let me now, on the graphic blackboard that you see on the screen, let me make a very first sketch. So let's suppose that we have a groin which is laid over a foundation. This is the foundation of the groin. And we have a groin that has this typical shape with sided, with sloped side. And this is a very rough sketch. So the slope of the sides is exaggerated. Actually, it never goes. Usually the slope is, let me say, usually this slope is less than 1,1, which means that this angle here is less than 45 degrees. Okay. So what is our problem? Our problem is, let's suppose that I have an isolated armor unit here. Let me change the color. Of course, here the slope is exaggerated, so it looks like this armor unit is unstable. But actually, I wanted to exaggerate the slope precisely because I wanna get a perception of what's going on. And what happens is that you may get a wave colliding with the breakwater, and then here you have the breaking usually, and then you have a run up, which is with the high velocity. The velocity of the run up can reach even 10 meters per second. It's really an important velocity. And then you have later on a run down. Reduced velocity. Good. And now you have two destabilizing forces. This is the destabilizing force of the rundown. So this is run down forcing. And let me go back to the blue color. You have also, of course, a run up forcing. So as I said, the run up is with a higher velocity. The run down is with the reduced velocity, but when you have the run down, you have the self weight of the particle, which is a destabilizing force. While in the run up, the self weight is a stabilizing force. So what we need to do in order to understand the process, in order to understand the physics of this process, is to study the equilibrium between these forcings due to run up and down and the stabilizing forces. Okay, so we need to look at the details of this unit and study the forces acting on it in order to see if the unit is stable or not. You may say that this is a very simple scheme, which is not realistic, because you may say actually units are not isolated. What do I mean? If I look to, 1 second, because I need to look back at the screen. Okay, good. If I look at this picture, you see that the units are not isolated. You see first that the slope is very mild here. It's a very gentle slope. But actually, when you build groins, you may have indeed slope that are significant. But besides the slope, you see that the units are not isolated. But let's start to discuss the physical process from a very simple scheme, from the very simple scheme of the isolated unit. And then we will study the effect of the so-called hiding, because these units being placed into a group, they hide each other. Okay, so first we study the equilibrium of the isolated unit, and let's take a very simple shape like the cubic shape, and then we will study the effect of hiding. Again, the purpose of this study is first to get a physical understanding. Second is to propose to you an alternative to the use of empirical formulas. Is to propose to you, the second purpose is to propose to you a physical criteria based on the rules of physics to understand stability. And then I anticipate that in the next couple of hours, in the second 2 hours, I'm planning to make an exercise to clarify, to apply both methods, empirical formulas and physical understanding, okay, and physical method. Now, in order to study in detail the stability of the Harbour unit, now let me draw a new sketch. So I go back to the blackboard here, and let me make a new sketch. So file, new. Okay, let me expand it, perfect. And now let's make this zoom on the unit, okay? Now, let me lie down the, first of all, the shape of the breakwater. So let's suppose that this is the foundation, and let's suppose that this is the side of the breakwater. Good. And let me make it less sloped, because otherwise it's not really realistic. So let me make it in this way. And let me indicate with the symbol beta this angle here. Let me reduce the thickness of my writing. Okay, now this breakwater, this groin is made by units, and let me depict some of them, okay? With irregular shape, maybe. Okay, let me make another one. Good. And now let me study the equilibrium of a single one isolated that is placed here. Okay, very, very simple shape, close to cubic. Okay, perfect. This is the unit whose stability we have to study. Okay, now let's first of all draw a force, a run-up force that is destabilizing the unit. So this run-up force, it's something like this one. Okay. And let's consider only the run-up now. This is the run-up originated by waves. Let me make it thicker because I want to make it very visible. Okay. Good. What is the value of this force? So this force, let's call it with the symbol F. It's equal to, we can write it in this way. Let's first of all assume that this force depends on the shape of the particle through a coefficient which we can call C2. So this is a shape factor. Okay, let me write here C2 shape factor, shape coefficient. Coefficient factor doesn't matter. And then this forcing depends on the shear stress, which is originated by the water running up. What is the shear stress? It's a tangential stress. It's due to friction of water on the side of the breakwater. So this is, as I said, the shear stress, which tends to push the elements, the units of the groin up. Okay. Okay, so we will see how to compute this tau. And intuitively, it depends on what? It depends on the velocity of water. If you have water that runs up very quickly, then you have a higher tau, okay? And then, of course, the force depends on what? On the size of the unit, precisely the square of the size, because the forcing depends on the exposed area of the unit, okay? And this exposed area can be computed depending on a characteristic dimension D. D is characteristic dimension, sorry. Characteristic dimension. So if the shape, the unit is cubic, like in this case, D can be the size of the cube, okay, the side. If the unit is spherical, D could be the diameter. What is important to remember is that D is a characteristic dimension, characteristic size, and the product of D times D squared times C2 gives the exposed area of the unit. And the exposed area multiplied by the friction factor gives the amount of this, sorry, the exposed area times the shear stress tau gives to me the final amount of the forcing that tends to bring the particle up. Very good. Now, the particle is exposed to this destabilizing force. Now, what are the stabilizing forces? First, we have the self-weight. And the self-weight is applied in the center of gravity. Just 1 second, let me see the size of my drawing. So it's applied in the center of gravity, and it's something that goes in the vertical direction. So this is the self-weight. Good. What is the amount of this self-weight? Let's call it W. W is given by, first of all, the weight per unit mass of the unit, and we have to take the immersed weight. So basically, W is equal to another shape factor. Let's call it C1. So C1 is another shape coefficient. Good. This shape coefficient multiplied the specific weight of the unit. If it's a rock unit, the specific weight may be something like 2,500 kilogram force per cubic meter. So let me write here. Gamma S may be something like 2,500 kilogram force per cubic meter, okay? And this is then equivalent to 2,500 times 9.81 Newton per cubic meter, okay? We have to subtract now the specific weight of marine water. Gamma is specific weight marine water. It depends on the salinity, but this is something like, more or less, could be something like 1024 kilogram forces per cubic meter, okay? And so the difference between gamma S minus gamma gives to me the immersed weight. And to be conservative, we need to consider the immersed weight. You may say, okay, but the unit is not completely immersed. This is true. On the other hand, to be conservative, let's consider the case where the unit is completely immersed. And then finally, I have to multiply here the characteristic dimension d cube, because this is the mass. It's not the exposed area like it was before. I have to, the volume, sorry, I have to compute the volume of this unit, and the volume is given by the shape factor C1 times the cube of the characteristic dimension, okay? And this is the weight. The weight is directed along the vertical, and we can decompose the weight in two directions. So first of all, let me just do like this. I want to put this at a little bit lower position, because otherwise the drawing is not clear. Okay, let's suppose that the center of gravity is here. Now let's decompose this self-weight in two components. One component is parallel to the side of the groin here. Good. And the other component is perpendicular to the side of the groin. Good. Now let's compute these two components. This is first, let me say one thing. This angle here, this one is beta, okay? If you make a very simple trigonometric assessment, this angle is beta, and you can understand it very easily if you imagine, if you think of bringing beta, so the slope of the side, if you think of bringing this slope close to zero, you realize that the black beta, this one, is decreasing. Let's suppose that you take this angle black beta close to zero. You easily understand that it goes close to zero also the other purple beta, which means that they are the same angle. Now let me remove these circles. Okay, so the angle that I indicated with the purple line is beta. Very good. And therefore, it is, we can conclude, we can say that this force here is W sin beta. Okay, and this force here, the perpendicular component, is W cos beta. Okay, now we can study the equilibrium. And but before studying the equilibrium, let's say that first of all, the W sin beta, the component that is parallel to the side of the groin, is a stabilizing force with respect to wave run-up. This is clear because it's opposing the green force given by the shear stress. Very good. Now, what about the component that is perpendicular to the side of the groin? This component, perpendicular, it's also originating a stabilizing force for the effect of the friction. And this stabilizing force, we can write it in this way. So it's given by the perpendicular component, W cos beta, multiplied by what? By the tangent of the friction angle phi of the units. So what is phi? It's the friction angle of the units. Okay, so if you have this component perpendicular to the side and you multiply it by the tangent of phi, then you obtain a second stabilizing force, which is due to friction. Because of course, if the green forcing originated by wave run-up wants to move up, this particle has to compete with the self-weight, the component that is parallel to the side of the groin, but also has to compete against the friction, because you know, it's the friction is taking energy, and it's acting as a stabilizing force. And the friction is precisely given by, the friction forcing is precisely given by what I wrote here. Okay. Now, if I make then a sum of, let me go to blue, sorry. If I now sum to the friction plus W sem beta, which is the component of the self-weight parallel to the side, then this is the sum of the stabilizing forces. And I am interested in studying the limiting condition when the sum of the stabilizing forces is equal to the green destabilizing force. So I am interested in studying the equilibrium between W cos beta tan phi più W sem beta and what? C2 tau d square. And let me call this tau C. Why? Because it refers to critical condition. So tau C is the critical value of the shear stress originated by the wave run-up that brings the unit to limiting equilibrium. So basically, if I now rearrange this equation, if I take this equation and I rearrange it, I can rewrite it in this way. C2 tau C d square minus W sin beta divided by W cos beta tan phi equal to 1. This is the condition that I want to study. It's an equilibrium condition, and this is, we can call it condition of critical equilibrium. This is what I want to study. And look, we gained a physical understanding of how the process works. Yes, you may say, what happens when I have the rundown? When you have the rundown, the situation is very similar. You just have to change the sign of your F, of the green forcing. You have to change its sign. And then you have two destabilizing forces, because the self-weight in the direction, in the parallel direction of the slope becomes then a destabilizing force. And you have two destabilizing forces, the green one and the W sem beta, and only one stabilizing force, which is given by friction. So it is a very elementary change that you have to make to study the rundown. And then you may say, what happens if I have other particles? It's not isolated. Of course, if it's not isolated, then we need to make a correction. And we will see how to make this correction. Now, I am now interested in studying this value of tau C. So why I am interested in studying the value of tau C? Because as you see, tau C only depends on the size of the particle, only depends on the shape of the particle, okay? And tau C only depends on the slope beta, and then it's relatively easy to compute. And what we have to do is to check whether our waves during the run-up originate a tau that is greater than tau C. Tau C is the critical tau. It's the critical shear stress. If our waves originate a shear stress that is higher than tau C, then the conclusion is the particle is unstable. Conversely, if our run-up by waves originates a shear stress that is lower than tau c, we can conclude that the particle is stable. So now we have two steps to complete. The first is to find an estimate for tau c, and we have to apply the relationship written in red on the left part of the blackboard, left bottom part, but we can rearrange it a little bit. I think it is better if we rearrange it a little bit. Why? Because I can substitute for W the expression that you say here. So let me change the color. Let me take the yellow. So basically, I can substitute here and here what? This one. In order to get an expression that is easier to handle. So I have a first step to complete, which is to rearrange this equation. Okay. And the second step is to discuss how to compute the shear stress originated by waves. Very good. Now let's open new graphic blackboard in order to rearrange this equation. And what I have to do again is to substitute W in by following the yellow arrows, and I have to take the value of W that is given by the product of C1 gamma S minus gamma times the cube of the. Okay, let me open another one. The first, let me rewrite the equation in this way. So let me take the black color for now. Let me rewrite the equation in this way. Let me make sure that I'm not pressing the buttons of the pen. So C2 tau c d square minus W sem beta. This is equal to W cos beta tan phi. Okay, this is simply rewritten. Now let's remember that W is equal to C1 gamma S minus gamma d cube. Okay, let's now substitute W, but let's write it in this way. Before making the substitution, let me rearrange a little bit the equation. C2 tau c d square, it's equal to W, which multiplies sin beta plus cos beta tan phi. Please check if everything is correct, but I would say that so far so good. Now I can make the substitution. So C2 tau c d square, it's equal to C1 gamma S minus gamma d cube times sin beta plus cos beta tan phi. Good. Now we can write it. First of all, let me say that I can cancel out the square and the exponent of the t at the right-hand side, and I can write it in this way. To get an explicit expression for tau c, I can write it as C1 divided by C2, which multiplies gamma S minus gamma d, and then I think I can take as a common factor cos beta, and then here I have between round parentheses sin beta divided cos beta is tan beta plus tan phi. Okay, I think this is fine. Now, C1 and C2, these depend on the shape of the particle. Only depend on the shape. And so let's take C equal to C1 divided by C2. It's a third shape coefficient, which results from the combination of the previous ones. And then I can write the resulting equation in this way. Tau C, it's equal to C. C, yes. Gamma S minus gamma D cos beta tan beta plus tan phi. Now, in the very simple case, beta equals 0, what we obtain is tau C, it's equal to C gamma S minus gamma D, and precisely it's tan, let me see it as if beta equals 0, we have, yes, sin 0, okay, tan phi. Okay. So this is the final equation, and we can write it in this way. And just 1 second. Okay. We can write it in this way. Tau C, and let me change the color because this is an important conclusion. Tau C divided by gamma S minus gamma D. Okay. This is equal to C tan phi, which is something which we may say it's constant. And look, this number here, it's a dimensionless number. What is this number? This number is a characteristic of the critical shear stress and the unit, which means that this number, which is a constant, gives critical conditions for a unit of given size depending on the shear stress. And given that this is a dimensionless number, it's clear that it does not depend on the dimension of the unit. So it is a number which is, or let's say, it's a number that we can study and which represents the conditions of stability for units regardless of their size. And given that this is a dimensionless number, what comes out is that if we, in a experimental way or in a physical way, if we can find a relationship to describe this number, then if we find an estimate for this number, let's suppose that we can find a value for this constant, which is a constant across different sizes of the unit. Okay, so let's suppose that we can find a way to estimate this constant, and the way can be experiments in the lab or in the field, or the way can be a physical reasoning, a theoretical demonstration. But if we can find the value of this constant, then we have solved our problem, because once that we know the shear stress originated by waves, then we can, through this number, through this constant, we can estimate the size d of the units that I need, which is perfect. I mean, I make again this conclusion. This dimensionless number, which is constant, if I were able to estimate it, then I would have solved my problem, because depending on the shear stress originated by waves, which I can plug in this equation instead of tau c, then I can, depending on the shear stress, estimate the size of the units that I need for critical conditions. And then if I want more stable condition, I can increase the size of the unit. But basically, this demonstration gives to me a way to check the stability of the rock and armor units. Now, you may say, look, this computation that you did is very simplified, which is true. It is indeed true that it's simplified. And what are the assumptions, the simplifying assumptions that I introduced? For instance, I am assuming that the coefficient C2, which is a drag coefficient, is a coefficient that relates the shear stress to the forcing. We assume that this C2 is a constant. Actually, it's not a constant. It depends on the forcing. So it depends on the fact, it depends on whether or not the particle is fully submerged rather than partially submerged. So basically, it's a simplification, the fact that I assume the C2 constant. And then you may say, for instance, that I assumed that the particle is fully submerged, while probably it's unlikely that it's fully submerged. So another approximation. Now, what could be a way of inspecting with more detail, with more rigor, this process? Actually, there is a theoretically based analysis that I could carry out in order to deepen my knowledge. And what is this theoretically based analysis? It's the dimensional analysis. You may have heard already about dimensional analysis, the Buckingham theorem. Dimensional analysis basically starts from the identification of the relevant physical variables governing a process. So we first have to identify what are the physical variables driving this process, and then we have to identify their physical dimensions, their units. So these physical variables do include only in their measure units length, then it's a geometric problem. Do these physical variables include length and time in their units? Then it's a kinematic problem. Do these physical variables include the three fundamental dimensions of physics, mass, length, and time? Then it's a dynamic problem. And let me make just a quick note here. Give me 1 second, students, that I have to answer this call, but really a second to postpone it. Pronto? Sì, perfetto. Allora, guardi, io ho lezione fino all'1:30, adesso sto proprio facendo lezione. Possiamo sentirci quando faccio il break tra mezz'ora. Se vuole tra mezz'ora la richiamo. La chiamo a questo numero, va bene? Perfetto. Grazie a lei, buongiorno. Buongiorno. Sorry, students. University administration. I was saying I want to write down something here in order to fix in your memory what I just said. So what is a way of making this analysis more theoretically based is dimensional analysis. Dimensional analysis. I anticipate that we are not doing it in detail. I just want you to know or to recap this possible solution. Okay, it's a way of analyzing the dynamics, kinematic, and geometry of physical processes. So you have to analyze the dimensions of the governing variables. Dimensional analysis is governed by the Buckingham theorem. What does it say, the Buckingham theorem? Okay, now, if you have a physical process which can be translated into a physical meaningful equation involving a number n of physical variables, we will see later what the physical variables are in our case. So let's suppose that we have a process, a physical process, involving a number n of physical variables, and let's suppose that these variables have k dimensions. The dimension examples are length, time, mass, for example. Okay. Then the Buckingham theorem says that the process can be described in terms of a set P equal to n minus k of what? Of dimensionless numbers. Look, this conclusion is quite interesting for us because in this relationship here, I already identified a dimensionless number. So without knowing anything of the Buckingham theorem, without starting from the point of view of dimensional analysis, I already came to a conclusion which says that a dimensionless number is a constant. Okay. Now, if I then look at the Buckingham theorem, what I can say more with respect to what I already achieved, what I can say more is that actually this constant, I can express it in terms of a dimensionless number. Why? Because let me consider what are the physical variables governing my process. Okay, and so let's see how many dimensionless number I need to describe the process. Now, if I look at the physical variables, these are tau c, describing the process, comma, gamma s minus gamma, describing the process, rho, mass density of seawater, d, the dimension of the units, v, the velocity of the fluid particle that is colliding with the Harbour unit. So n, it's equal to 1, 2, 3, 4, 5, and it's equal to 5. If I look at the dimensions, how many they are? They are k, it's equal to 3, precisely, mass, length, time. Good. Then what can I say? I can say that P is equal to 5 minus 3 equal 2, which means that I can describe the process with two dimensionless number. One is here, and the second one, the second must be here. So it's not a constant, but it's a dimensionless number. Now, we don't make the dimensional analysis, but I want to go to the conclusion. So let me just delete something. And let me delete something here to gain some space. Be patient. Okay. Okay, so let me make this conclusion. And let me take the red color. So two dimensionless numbers. 1 second. Okay, very good. And select none. Okay, two dimensionless number. Okay, then I can write the equation in this way. Tau C divided by, sorry, gamma S minus gamma D. This is equal not to a constant, but it's a function of another dimensionless number. What is the dimensionless number? Let me jump to the conclusion. We are not making the demonstration of the dimensionless analysis. The dimensionless number is called sediment Reynolds number. This is the unit, sediment unit, it's a synonym, unit Reynolds number. Very good. What is this number? How can I write it? Okay, it's dimensionless. So it's given by, I put the kinematic viscosity of water at the denominator. I put the size of the unit at the numerator, and I put the U star, which is the shear velocity, at the numerator. How can I express the shear velocity? The shear velocity is equal to the square root of tau divided by rho. And the rho is density seawater. Seawater, perfect. And then Ni is kinematic viscosity. Viscosity of seawater. And I think that everything else is known. Okay, so your question now is, what should I remember to prepare my exam? You should remember this. Let me change the color. You should remember this relationship here and how we derived it. So how we derived, in particular, this one here. This is something that you have to remember. And then you have to remember that it's not a constant. The dimensionless number here, it's not a constant, but it's a function of the Reynolds, the particle Reynolds number. If you remember how to compute the particle Reynolds number is better, but it's not strictly needed. Okay, so because I understand that there are already many things that you have to learn by memory. I don't want to exaggerate, but if you remember, keep in mind that the particle Reynolds number, which is also called the sediment Reynolds number, it's an important behavior of units exposed to possible transport, sediment transport. So it's better if you indeed if you know something about this number, the particle Reynolds number, and if you remember, of course, how it is computed, or at least what are the variables determining it: kinematic viscosity of water, shear stress, and mass density of water, that would be better. But of course, I understand that you cannot learn by memory everything. Now, we didn't solve our problem because still we don't know how to compute this this number here. I am circling in red. We don't know how to compute it, because we have learned that in principle we can say it's more or less a constant, but actually with a theoretical analysis we concluded that actually it's not a constant, it's a function of the particle Reynolds number. Now let's come to the very technical and professional question. Okay, no matter what is the driving variable of this number, I need to estimate its value, okay, depending on the particle Reynolds number. And this same problem was the problem that people about 100 years ago had to solve, because this demonstration that I now explained to you, I lectured it to you, this demonstration was already carried out about 100 years ago by engineers that wanted to study precisely this problem. It was in a different context, not in Harbour engineering or coastal engineering. It was in a different context, but it was the same, precisely the same problem. So engineers, they came to the conclusion that this number with the red circle in the bottom left of my blackboard is important. It depends on the Reynolds number, but they gained an expectation that shouldn't vary too much, okay, because under simplifying assumption, they understood that it is more or less constant, but they had to estimate it. And, you know, to estimate it, it's not easy. And what they decided to do, they decided to make lab experiments. And this was done by a guy whose name is, let me change the color, whose name is Shields. This guy, in around 1930s, this guy made a series of lab experiments to study what? To study this, precisely this number and the values it assumed. And in fact, this dimensionless number was called, and it's still called, Shields dimensionless number. Good. Okay, so what did Shields do? I am aware that I have 10 minutes to go before the break, so just give me now this time to introduce the experiment by Shields. And what did Shields do? Okay, let me open a new graphic, a new sheet in my blackboard. Now, Shields tried with flume experiments. First of all, I think you know what is a flume, but I will show you a picture in just 1 second. Shields, with Flume experiment, wanted to study the relationship between a graph, relationship between two-dimensionless number, which we just discussed. Give me 1 second. So he put the Reynolds star in the abscissa and the Shields number in the ordinates, tau divided by gamma s minus gamma d. So basically, he built different flumes in the labs with particles of the different diameter. So he started with particle of several sizes, and then he what he did was to run a flow in the flume, and for each trial flow he computed the couples of Reynolds particle Reynolds number and Shields number. Okay. He varied the velocity of the flow until he saw that the particles started moving. And then he was able to draw some points in this graph. And what he did, indeed, was to make a lot of experiments, and he found several points, okay? And he found something like this. I will show you a picture in a moment. So what he found was that for very low Reynolds number, there is viscosity dominating. So a low Reynolds number means, if you remember the particle Reynolds number, how it is computed, Re star, it's equal to U star B divided by n, and U star, it's equal to tau divided by rho. Okay, what happens if you bring Reynolds star down, low values? Of course, you have to decrease U star. How can be U star decreased? By decreasing tau. How can we decrease tau? By decreasing the velocity. So if you have the flow with reducing velocity, then of course less energy, which means less friction, less tau. So when the velocity is very low, the Reynolds number is very low, and there is viscosity dominating. Viscosity actually drags a lot. And this is why he found that there was an increase of the Shield number for low velocity. And then for increasing velocity, he found a minimum. And then, strangely enough, he found, you see here, an increase of the Shields number for increasing turbulence. But after a while, he came to a plateau, constant. Okay, so the Shields number remained constant for increasing Reynolds star after a certain limit to turbulence. This is the domain of turbulence. Okay, and what is this constant value? Look, this confirms that indeed the Shields number is more or less constant when the flow is highly developed. And what is the value of this constant value here? It's about 0.056. Actually, the range is about 0.03, 0.06. So what he found experimentally is really interesting. If you are in the domain of turbulence, and when we have waves hitting a groin, we indeed are in the domain of turbulence, the Schiltz number is close to constant. Let me show you, before we make the break, let me show you a graph of the original diagram by Schiltz. So let me take this. Here it is. This is the original Schiltz diagram. So you see that here it's not clearly legible, but if you look at where my mouse is pointing now, let me see. Yeah, you see my mouse. It's 0.05. Okay. And here are the points, the experimental points. And also this analysis was repeated by many scientists. And then, you know, they concluded, and it's written here, you see, Schiltz parameter or Schiltz number assumes values ranging from 0.03 to 0.06 for turbulent flow. But again, our domain is the turbulent flow. Now, what can we conclude? We can conclude that what is written here, the Schiltz method can be used to evaluate the stability of sediment into the sea. In fact, given the hydrodynamic forcing acting on the Harbour unit, one can estimate the shear stress tau on the unit itself, and then the resulting Schiltz parameter. If the latter is lower than 0.06, then one may conclude that the unit is stable. And this is what we want to do. So now we have only a final step. And the final step is to compute the shear stress tau originated by waves on the side of a groin. But actually, the results by Schiltz are very interesting. I think we can define this analysis that was made by Schiltz as a physically based analysis. Then you may say that the conclusion is supported by empirical experiments. In order to determine this value 0.056, we had to rely on physical empirical experiments. Yes, I agree, but still the essence of the method is physically based. I think it is time to make a break now, and I wonder whether you have any question. Okay, as you may notice, I try to follow your suggestion and to work on the graphic blackboard. My personal feeling is that probably this is better, but I don't know. Okay, let me just
yes, for me was really better. Thank you.
Okay, thanks a lot. I think no, your suggestion was very useful. Okay, very good. Let's make a 15 minutes break. And meanwhile, if you have any question, you can write on the chat. So let's meet again at 11:30. Thank you. Enjoy a coffee if it's possible. Okay. I am almost ready. So, recording is still going on, and of course you will need to skip the break. Okay. Questions? No questions. Okay. I also would like to remind you that if you want to deliver presentations, you have 2 lectures to deliver them. So I would be very pleased if you took this opportunity. Also, it would make our 4 hours a little bit more, let's say, articulated. It's not only me talking, but I give the word to you for 10 minutes and then the discussion. It is more more productive, and you may wonder what you could talk about, and I am sure that you have something interesting to say, something that you saw, something that you studied. I am sure. So I mean, preparing 5-8 slides on something that you may take some time to study, a case study, a problem, or something that you would like to know better. You know, I think for sure any of you has something to say that may be interesting. And in the past, when we did this, it was very productive. Okay, now let me share the screen, and just 1 second. I need to see the blackboard. Okay, let me share the screen. And oh, before sharing the screen, so now what is our next challenge? The next challenge is to estimate the shear stress given by waves. And so let's try to solve this in a simple way. And let me share the screen with the blackboard. Just 1 second, I need to look at the phone as well, because, you know, I need to check what you see. Otherwise, I always have the doubt that you don't see what I think you are seeing. So let me open a new sheet in the blackboard. Good. Now we have to then to estimate tau. Okay, this is our question mark now. And of course, we know the forcing of waves, etc. Okay, and let's first say that we refer to groins, but in general, groins or breakwaters, but in general, keep in mind that the shear stress does take place in a marine environment, all the time. I mean, the coastal engineering, harbor engineering is all about interaction between waves, currents, sea bottom, ships, berths. So everything is about interaction of water and structures. So, I mean, the shear stress, it's not only taking place when a wave hits against a groin. It also takes place when waves moves in the ocean, and the shear stress is in the bottom, over the bottom of the ocean. It takes place when waves hit against port structures, whatever. So we need to make a general treatment of this. And a general treatment basically suggests that tau can be given by the sum of two components. So let me just write tau is given by the sum of two components, and there is a tau given by currents, let me call it tau Cu, plus a tau given by waves. Okay, this is the general approach that is followed in Harbour engineering. And so what is originating the shear stress? It's the movement of water relative to the surface. So if it's the groin, it's movement of water along the side of the groin. And if it's sea bottom, is movement of water with respect to the sea bottom. And so the shear stress is originated by velocity of fluid particles that are moving with respect to the opposing surface. And precisely, we can write that tau, and let's refer to currents, it's given by a classical formula in hydrodynamics is 1/2 rho density of seawater, and then you have a friction factor we can call FCU, and then you have to compute let's call the velocity u prime, the velocity of the current, you multiply by u prime square. So the shear stress again depends on the square of the velocity of water relative to the opposing surface. And then there is a friction factor, and then there is the density of water and the coefficient 0.5. And for waves, I have a similar formula to tau w. It's equal to 1/2 rho FW, friction factor originated by waves. And here, let me call it capital U prime square. Now, here, the friction factor is, let's discuss it later. It's relatively simple. Let's say that this is something that we can estimate basing on the literature. So this one and this one. The density of seawater is not a problem. We know it. And now we have to discuss how to estimate these two velocities. Okay, let's forget about currents, okay? Because if we focus on groins, yeah, you know, the forcing, the friction originated by currents is negligible. The friction originated by currents may be important if we refer to the sea bottom, may be important if we refer to offshore structures, but for a groin, you know, it's not really, the current is not really, we can forget about it. So let's now focus on TW, and so how to estimate the velocity of water against the structure. So there are two ways. So about U, capital U prime, there are two ways. You may refer to the orbital velocity of fluid particles, and this is before breaking. So you know that before breaking, waves imply a transfer of energy, not a transfer of mass. But still, there is a limited orbital velocity which causes some particles to move. And let me show you just 1 second a picture. So let me share the screen, and then let me go, sorry, here. I'm sorry. Let me go here. Okay, new page. I am opening my website and then I need to open a page. Give me 30 seconds. Coastal engineering and let me see. Give me 1 second because I need to find it. Or maybe it's okay. Okay. This is a lecture that I didn't teach to you about the dynamics of sea waves, and just 1 second. Okay, here it is. This is the figure that I wanted to show you. So you see before breaking that waves imply only a transfer of energy, but you see the orbital velocity of the fluid particles. This orbital velocity is much lower than the velocity of propagation of waves, and brings fluid particles close to the surface to slightly advance. The orbital velocity decreases with the increasing sea depth. So if you have very deep sea, there is no relative velocity of particles in with respect to the sea bottom. But if the sea is not deep, then there is this orbital velocity which is frictioning against the sea bottom. Now, this is before breaking, but after breaking, you know that the waves from a transfer of energy, they turn into transfer of mass, and then the fluid particles gain a lot of velocity. And after breaking, given that we are now focusing on groins, so let's forget about the orbital velocity, but let's instead focus on what happens after breaking, because when the wave approaches the groin, typically it is after breaking. Okay, you may say that if the groin is very long, then at the toe of the groin offshore, you may have the friction between waves and the groin before breaking. But in this case, in any case, the friction it's much lower than the friction that takes place after wave breaking. So really with groins, we are not interested in estimating the shear stress induced by the particle velocity. We are interested in estimating the shear stress after wave breaking, and therefore we have to be able to estimate the velocity of waves after breaking. Okay, perfect. So let's forget about this figure and let's go back to our just 1 second, Blackboard. Give me 1 second. Okay, okay, here we are. Again, the Blackboard. Good. Okay, so in my web pages, you can also find a formula for estimating the orbital velocity, but it's not important that you remember it. Okay, now, so how can we estimate after breaking the velocity of particles? It's estimated through empirical relationships. I found an interesting contribution which gives an abacus, which basing on experiments, lab experiments, and real field experiments, gives an idea of what is the run up and run down velocity on a groin side. This contribution is not open access, so I cannot show it to you, but we can look for it in the web and download it. I cannot put it available with direct link on from my website because it's not open. Now let's then find this contribution, because we really need to get an idea of this velocity. Okay, so let me just share the screen here. Okay, good. And let's look at this contribution, which is described here. Okay, after braking, look at this sentence. After braking, the velocity of particles can be computed through empirical relationship by distinguishing between run up and run down along the side of the groin. And there is the reference. Schutfroth et al. I don't know how to pronounce it, 2001. Let's look at the list of the references and then let's find it on the web. Okay, this is the contribution. And so how we can find it? Let's copy the title. Okay, so I take this title, I copy it, and then I open a new page. I go to Scholar. I go to Scholar and I put the title in, paste, and here it is. Now you see that there is a link to the PDF on the right. The fact that a PDF is available on Scholar doesn't mean that it's open access, but in any case, it gives us the opportunity to open it. Okay, so let me see if I can open it with this default program. Yes. So you see, let's look at this paper. And it's run up velocity at a breakwater. It's an experimental breakwater. And it is quite a simple paper that explains some measurements that they did. And also there are some nice figures of the breakwater. And it's actually, this is not the original paper that I wanted to open. So let me see. This is just a short summary. So the short summary doesn't say much, actually. So let me go back to this paper. And let me see if I have it already, because actually, it's not openly available. Let me see if I have it already. So just 1 second. Otherwise, I'll open it from another location. So it's, I think it's here. Let me see. I don't think. Let me see if I can. Maybe this one. Let's see if it is this one. Yes, it is this one. This one was found by me through the internal library. And I meaning that you have access to this paper. If you look in Scholar for it, and let me just check if this is possible. If you look in Scholar, so I have to change the reference actually, because yeah, it's the same title, but for some reason I don't know why it only shows. Let me click on the title, so I don't go to the PDF, but I click on the title. Let's see. Okay, and here we are. Here we get to the journal where the paper is published. If you click on download and you click on it from the internal network of the university, be careful. Now I am at home. I'm not at the internal network of the university. But if you click on download, you see that you get the price here. Because why do I get the price? Because I'm not in the internal network of the university. But if you click over it by staying in the internal network of the university, you have access, because we have access to this journal from our library, so you can find it. I just wanted to discuss with you how references can be found. Now, let me look at this paper by looking at what I downloaded from the internal location of the university. And what I'm interested to show you is the experimental setting. You see, this is the breakwater, which is, I mean, in this case, what is found for the breakwater applies to a groin. There is no much difference because, you know, the difference is just in the displacement of the structure, but they are built in the same way. And when they are hit by a wave frontally, they are, I mean, they behave in the same way. Now, let's look at the abacus, which I wanted to show to you. These are the description of the measurements, and you see the units, how they are done, and etc. So basically, let me move forward to get to the abacus, because I think it is interesting to give an order of magnitude. So look at this figure. There is the vertical distance to surface water level. So the vertical distance, and here you have, what does this mean? It's the vertical distance along the slope of the breakwater, okay? So here we see that the waves that they considered can climb the breakwater up to a height in the vertical direction of, let's say, 5 meters. Good. And here you have the wave run-up velocity. So basically, this abacus tells us that if you have a structure and a wave that is able to generate a run-up up to 5 meters, then the velocity that you get is given by these curves. So this means that as long as you climb up, the velocity decreases, of course, and the velocity gets to 0 when you reach the limit of the run-up, because of course in the limit of the run-up you have velocity that becomes 0, and then the run-down starts with a velocity in the opposite direction. So basically here you can see that in this breakwater, where the wave height is related to 3 meters, the wave period is 8.5 seconds, and the slope is 1 over 1.5. So this is an example which refers to this particular behaviors. So wave height of 3 meters can originate a run-up up to a vertical distance of more than 5 meters and can originate a run-up velocity of maybe 10 meters per second. 10 meters per second is really a lot. You know, it's really an impressive velocity. So basically, this gives to you an order of magnitude. So of course, it refers to this specific example with a wave height of 3 meters, but it gives you an idea of what are the velocities into play. So you can use these abacuses for estimating the wave run-up and the run-up velocity. The run-down velocity is much lower. Okay, very good. Now let's go back to our original problem. And our original problem then it's given by, let me go back to the Blackboard. Let's go back to our original problem and let's use these relationships here then. So what is our original problem? It's estimation of the velocity of the wave run up. And this is given, given, then we learn that it's given by specific or empirical information. Very good. So let's suppose that we have it. So if we have this velocity, then we can estimate the shear stress. And but we need to know what is FW. FW, let me draw another arrow here, is again given by empirical relationships. I will propose to you an exercise which, if I well remember, it gives FW equal to 0.1, but we will see, okay? And in my web pages, you find also an empirical relationship, and which gives the value of the friction factor depending on the roughness of the groin. But again, what we need to refer to is to indications by the literature instead of using relationships, which you know, may be very empirical. What I suggest to you is to refer to who is providing the units. So basically, the producer of these units, for instance, if they are tetrapods, can give to you an estimate of FW, or you may indeed refer to the literature, and the literature it's also the source of the information that I am providing on the web pages. But again, this is an empirical coefficient that you need to estimate by possibly referring to direct information, which means producer of the units, or yes, empirical relationships. Okay, so at this stage you can compute TW, and then you can compute the value of the Shields number, because when you have tau, remember your Shields number, it's given by tau, in this case tau W, divided by gamma S minus gamma per D. And then you have to check that it's less or equal than something around 0.05. But at this stage, there is an additional thing that you have to consider, which is the slope. Okay. So it's clear that you know, the experiment by Shields were done by referring to a very gentle slope, something like this, with a unit placed here. And Shields found that Shields number is equal to 0.056. But what happens if you have a much higher slope? Of course, you have to correct the Shields number, because the critical condition is reached for a shear stress that is lower than what you estimated for a very gentle slope. So our next topic is, let me open a new page. Our next topic is estimation of the effect of slope. Okay. Effect of slope. Everything is described on my web pages. Don't worry about this. Now, what we can do is to compute a new critical, a new tau C, a new critical value of shear stress. And what we can do is very simple. We can express this new shear stress as a function of the shear stress with critical shear stress with no slope, and we have to multiply this value times two coefficient k beta 1. Now k beta is correction factor it's the correction factor for the longitudinal direction. What is the longitudinal direction? So let me refer to a beach with a groin, okay? So let's suppose that you have a beach here and you have a groin here, okay? This is offshore. This is offshore, okay? So let's suppose that in this case, let's identify with the longitudinal direction, this one. This is longitudinal direction. It's longitudinal with respect not to the groin, but with respect to the waves approaching the groin. And this is the transversal direction. Okay, so given this scheme, K beta is correction factor for longitudinal direction. K beta 1, it's conversion factor for the transversal direction. Yes, because the groin can be sloped in the two directions. Usually in the transversal direction, we don't have slope. So let's forget about this, okay? And then we get TC1, it's equal to K beta for TC. Okay, so what is the value of K beta? It's a slope correction factor. We have to make a difference between the run up and the run down, because of course the slope correction factor must be different in the two situations, because clearly with respect to the situation where you have no slope, you pass to a situation where you have a slope. This situation is, with respect to the run up, it's fine. I mean, it is opposing more resistance with respect to the no slope. But when you get the run down, then the correction should be a penalty. So when you work with respect to the run up, the correction should be an increase of TC1 with respect of tau C1 with respect to tau C. But when you look at the run down, the correction should be a penalty. So tau C1 should decrease with respect to the tau C. So let's then give two formulas for the correction factor, K beta. Let's write it for the run down. Okay, and this is equivalent to what? It must depend, of course, on beta. Okay, so it can be written in this way: sin beta phi, friction angle, minus beta, divided by sin phi. Okay, and you see that if beta is 0, the correction factor is 0. Okay, and in this case, the correction factor is lower than 1. If you look at these angles, the correction factor is lower than 1. What happens for the run up then? I am expecting that the correction factor is different. K beta is equal to, very similar, but it's phi plus beta divided by sin phi. And this is greater than 1. We will see with an exercise, greater than 1. And this is lower than 1. Okay. Good. Now we are ready to apply the Shields criteria. In this case, of course, we need to be told what is beta, what is phi, what is the FW, the friction coefficient, etc. We need to know what is the forcing, wave height, wave run-up velocity, run-down velocity, and then once that we have these informations, we can apply our Shields formula. And there is something that we didn't discuss yet, which is the effect of hiding. So we discussed the effect of slope, but we didn't discuss the effect of hiding, and which is strictly related, the effect of the unit shape. Let me discuss this later because this is very descriptive. I'm not providing any formula for discussing about hiding and etc. What I want to do now is now to recall to you the Hudson formula. I think that you already saw it. Let me open a new sheet in the Blackboard. And let's now discuss the Hudson formula. The Hudson formula, there is a link to a Wikipedia page which is very useful, and I will show the link to you later. Now let me just write it down because it's an empirical formula. You don't need to learn it by memory for the exam. It's an empirical formula and it is expressed in this way. W, which is, what is W? W is the weight of armor units of a single one. Okay, this must be greater than what? Okay, gamma R H, capital H cube, and then, sorry, there is a coefficient KD times gamma R minus gamma divided by gamma cotan beta. Okay, so what is gamma R? Gamma R is the specific weight of units. Okay, something which may be 2,500 kilogram forces times cubic meters. Okay, and then you have H is a significant, it's not significant, a reference wave height, reference wave height at the toe of the side. And this you can take something like 127 significant wave height, and you know what is a significant wave height. So basically you take the significant wave height and then you increase it 27% in order to get a reference wave height to be plugged in the Hudson formula. Now KD is a coefficient, KD coefficient, it depends on the units, on the shape of the unit, etc. It is in the range, let's say about 310, okay? And usually it is given by the producer of the units and etc. And what we can say of KD is also that it can be computed with an empirical relationship that can be written in this way. We can introduce a parameter NCR, called NCR, which is equal to 0.8 KD cotan beta elevated to the power of 1/3. And if NCR is given, and NCR, it depends basically on strictly depends on the shape of the armor unit, and KD also depends on the slope beta. NCR is a typical parameter of the armor units, and once you know it, if the producer can give you KD for specific beta values or the NCR value, and then from NCR you can compute KD. So at this stage the Hudson formula is completely defined. Okay. You see that it's quite different with respect to the shield parameter, because we don't have, we have no velocity here, okay? We have no velocity. What is taking the place of velocity? It's h. So in this case, you just need an estimate of h, reference wave height, which can be derived by knowing the significant wave height. And then you don't need to compute the velocity. So you don't need to refer to the abacus that gives to you, depending on the wave height, the run up and run down velocity. Also, the Hudson formula, you see that it doesn't make any difference between run up and run down. So it's more simplified. It's interesting maybe to see what a comparison with the Sheets criteria, okay? And to make this comparison, I am proposing to you an exercise. But before we go to the exercise, let me just share for a couple of minutes the screen of my web page, and let's discuss about hiding. So, what is hiding? Hiding is a kind of effect that you obtain when you assemble particles, units of maybe different size, and some of the units gets hidden behind larger ones. Or the size may be even the same, but still, if you have a unit that is placed behind another one, you have an hiding effect. And hiding, it's taken into account in the Sheets criteria by correcting the limiting shear stress. And again, we have a correction factor that can be applied. Usually hiding is not considered for the sake of being conservative when designing coastal structures, okay? So let's forget about it, but just be aware of the fact that hiding is usually an essential component of the Sheets criteria. Now, the shape of the armor units, it originates something that is very similar to hiding. So if you use tetrapods instead of regular cubic shapes, for instance, or tetrapods instead of almost close to spherical shapes, then you get a situation where the units get in a way tightened each other's and each other, and then you have more resistance. So what you have to do is to correct again the Shields factor, okay? We are not discussing in detail this, but keep in mind that usually the producer of the units can give you indications, because usually the producers, they make experiments in their own lab, or they may commission lab experiments in order to be able to give indications about the functioning of the units in terms of stability. So this is the source of information you have to look at. Let me just open this link, tetrapods, in order to show you the various shapes that tetrapods can take. And here you have figures. This is a figure of you know, tetrapods in their just produced, ready to be distributed. And here you see tetrapods in place. These are revetments, so they are they have the function of protecting the seawall in this case. Here you see again tetrapods protecting a seawall. And here the picture which I used to my web page. And here there is another example. You know, the looking is not really nice, but still it's not so horrifying, let me say. Okay, and but we are not considering this effect, as I said. And now let me show you. This is the Hudson formula described in my webpage. I want to show you the Wikipedia link to the Hudson equation. This is relatively recent, and you see that there is an explanation of the formula and also an updated version that is presented here. And it's an interesting reading, I think, if you have to apply it. And it's a useful complement to what you find here in my web pages. Okay, now let's try to look at an example of application. We have this last 45 minutes, and let's see to the exercise. Let's look at the exercise that I want to propose to you. So the exercise, if you go back to our tutorial page, it's placed here. I placed it yesterday night. So assessment of stability of Harbour units. Okay, and let's look at the, oh, interesting. Let me see why it doesn't work. Let me, give me 1 second. I make it available to you soon. Okay. One second. You have to understand why. I think it's a problem of permission. Okay. Interesting. If I cannot solve it, I won't take your time for long. If I cannot solve it very soon, I think it's better if I let me solve the problem later. And now I am opening it from my local PC. So let me see. Okay, I think it is this one. Good. And it will be available also on my webpage, but after I close the lecture, otherwise it takes too much time to me now to solve the problem. So this is an exercise which refers to a groin with side slope of 30 degrees, which is exposed to a significant wave height of 2 meters at its toe. The wave forcing originates at top wave run-up velocity of 4 meters per second and a top wave run-down velocity of 1.5 meters per second. So you see that the run-down velocity is much lower than the run-up one. The value of the wave-related friction factor FW is 0.1, which is plausible value for large stones, while the density of seawater is taken to be 1024 kilogram force per unit per cubic meter. It is assumed that the tidal velocity is negligible. Okay, so we also the tidal and current velocity is negligible. The groin is protected with boulders with characteristic size D 100 centimeters and a specific mass of 2,500 kilograms per cubic meter and a friction angle of 40 degrees. Now, it is required to verify the stability of the armor units with respect to the run-up and run-down by using the Sheets criteria, by assuming that hiding effects and effects of armor shape are negligible. And then there is the second question: verify the stability of the armor unit with the Hudson formula by assuming that NCR is equal to 2. And we assume that the producer gives us the value of NCR. Good. So I think that we can do it by Excel, okay? And then if we will have time, we will also do it with R. But let's start with Excel. So let me open an Excel file. So let me see. I would say let me go to Office. Here, and okay, and let me open an Excel file. Okay, this is not really what we want because this is already file. Just 1 second. Okay, let's work on this one. Let me make a zoom. Very good. And let me expand the first column. Okay, and then 1 second. I need to. Okay, so let's put a title here, and the title may be Exercise Harbour Engineering Ability of Armor. Armor doesn't make any difference. You can write armor or armor. It depends on the UK or American English. Okay, good. And now let's put all the information that we require. So the slope of the side of the groin, this is 30 degrees. It's much better also if we express it in radians. So plus 30, oops, sorry, plus okay, let me write B4 because I'm working online, plus B4, very good, divided by 180 times, I think, P Greco. Okay, sorry, F2 P Greco. Okay, and this is the expression in radians. If you can't follow me, you don't understand what I'm doing, just ask questions. Then other information, we have the significant wave height. significant wave height at the toe of the groin. I don't remember what is. Let me check. The significant wave height is 2 meters. 2 meters. Good. Now, top wave run up velocity. This is, if I will remember, 4. Let's see. I would say 4 meters per second. And then there is the top wave run down velocity. Top wave run down velocity. It's 1.5 meter per second. Good. And then there is the wave related friction factor FW, and this is 0.1. Sorry, I see here this cell. I need to use the comma as a separator of digits. Okay, very good. So now, and we have the density of seawater. The density of seawater is 1024, and this is kilogram divided by cubic meters, kilogram force. Okay, it's not in Newton. And now we have the characteristic size of the Harbour units, and this is 100 centimeters. Good. What else? Specific mass of the Harbour units, and this is 2500 kilogram forces divided by cubic meters. Okay, and then there is the friction angle of Harbour units. The friction angle is 40 degrees, and let me copy here the transformation in radians. Okay, good. And then we have the coefficient NCR of the Hudson formula. This coefficient is 2. Okay, these are our information. Okay, now what do we have to do? First of all, we have to compute the shear stress by wave run up, and let me write it in this way. Tangential tension, shear stress, it's the same thing, by waves run up. Now this is precisely, it's equal to, just 1 second, it's equal to 0.5 times what? Times the density of seawater. Let me see. Okay, density of seawater. And then I have to multiply it by the wave related friction factor. Then I have to multiply it by the run up velocity squared. Okay. Doesn't, what is the reason why it doesn't show the value? Let me see. It's the online version. I think this should be okay, but it doesn't work anyway. Yeah, I understand why. 0,5. Okay, very good. Now I get this tension. What is the unit? The unit is this is, let me think of it. This is given by the progress of 0.5 times the density of seawater in kilograms per cubic meter. Kilogram force, actually. No, this is density, so it's kilogram per cubic meters. And then it is computed by the wave-related friction factor, which is dimensionless, and the waves run-up velocity. I think this is given then by its Newton divided by square meters. So it is expressed in Newton because, and not in kilogram forces, just to make it clear. In this case, it's a density. So this is kilogram per cubic meters, and here it's a specific weight. So first of all, here I have to write specific weight. And here, to be coherent, I have to highlight that these are kilogram forces. And if I want to express it in Newton, I need to multiply it, to multiply it times 9.81, and this is in Newton. Computation that I made here for the tangential tension, it's Newton divided by square meters. Now I have to compute the tangential tension for wave run down. Good. For the wave run down, I have a similar situation, but it's now I have to take the run down velocity. So what I have to do is equal to 0.5 times let me go here, times density of seawater times friction factor times run down velocity squared. Okay, this is good. And so I have the two tensions. Very good. Now, what I have to compute? The slope correction factor. So the slope correction factor for run up. You remember the slope correction factor is different for run up and run down. And run down. So let's compute it. It is given by the sin, I don't remember, let me see, sin of, oops, sorry. Sin of what? Of the sum of the friction angle plus the slope. Okay. Good. Divided by sin of the only friction angle. Actually, I don't remember. I think for the run up, I should put here a minus. So let's see. No, it's not a minus, but it's because it's stabilizing in the run up. It's a plus. Okay, I think this is correct. For the run down, it's equivalent to sin. And there is the friction angle. Here it's minus the slope divided by sin friction angle. Okay, good. And you see for the run up is greater than 1, the correction factor. For the run down is lower than 1. And this is what we expect. Okay. Now we can compute the Shields parameter. So Shields parameter for the run up, and then here the shields parameter for the rundown. Good. Now the shields parameter for the run up is given by the tangential, equal, the tangential tension, very good, divided by gamma s minus gamma. So here I have to put gamma s 2500 minus gamma 2024. And let me see. Okay, I think in this case it's this is fine. This is fine. This is should be the specific weight of seawater, not the density. But if we assume that we take the values not in Newton but in kilograms, this is fine. In kilogram forcing, I can take the value of 1024, and let me. I need to then multiply here. Sorry, because okay. Let me complete the formula. Okay, this is to be multiplied here. Put it in Newton times 9.81. Okay, and then I have to divide it. Let me do it in this way. Let me the parenthesis here. Okay, and then I have to multiply it by the characteristic size of the armor units. Here it is. And I would say that this is divided by 100 because I have to put it in meters. Fine. And then I have to close the parentheses. I think here we are. Let me see. Let me count the parentheses. Yes, I think this is fine. But let me see what is the result. No, there is a mistake. I think there is something. Yeah, the parentheses, F2. Okay, and this is the shields parameter for the run up. And now let me, this is precisely equivalent to the limiting condition, and this was not made on purpose, but still I have to modify it because I have to introduce to divide by the correction factor. It's 1.46. So I get 0.0387, which means that the groin is stable, the unit is stable for the wave run up. Now let me compute the rundown. So plus, again, plus the tangential tension divided by, I open a parenthesis, gamma s minus gamma again. So let me open another parenthesis, minus 2024. Good. Times 9.81 times D. Good. Times D. And then I think I have just divided by 100. And then I close the parenthesis, and then I need to divide by the correction factor. Let's see if it works. I think it works. Now, let's look at the result of the shields parameter for the run up and the run down. They are both lower than 0.05. So we can conclude that it's stable. And let's create a condition to check it. So in order to automatically see if the unit is stable or not, the condition in Excel can be introduced with the function if. This is an Excel in Italian, so you see it visualized as a se. So let's put the condition. The first condition is that this should be lower than 0.05, okay? And if the condition is true, what I have to do is to put another condition. And then I have to look at this one, because I want to put a joint condition. I want to check whether both of them are lower than 0.05. So let me put the second condition. And then if both conditions are satisfied, B19 is lower than 0.05 and B20 is lower than 0.05, then I can write stable. Otherwise, it's unstable. Unstable. So I can close the second condition, and then I have to close the first condition. Unstable again. So it's stable. Let's put it in bold and in red. Okay. So this is the application of the sheets criteria. Look, you have this same Excel file available in my website. Let me show you. Example of the Excel file. I guess the link is broken. Yes, it's broken, but I now understand why it's broken, because, sorry, but let me check on my website, not on the mirror. I think it's broken because I'm referring to the mirror, but let's see. I'm not sure. This is not the mirror, but it's my website, the original one. For teaching, I use the mirror because the visualization is larger in the mirror. Let me see if it works. Yeah, you see that the links in my website already work. So this is the Excel file, which is available. I'm not opening it because I want to save time. So it's the same that I am doing here. Now, this is the sheets criteria. Let's see what happens if I reduce the size of the Harbour units, 80 centimeters. It's still stable, 70 centimeters, unstable, because you get in the run-up is unstable in the run-up. If I do 60 centimeters, it's unstable again in the run-up. 50 centimeters, I guess it's unstable for both of them, okay? So let's go back to 100 centimeters. It's stable, but let's look at the run-up velocity. Let's bring it at 5 meters per second. It's already unstable, and you see a lot unstable. So, because if you look at, not really a lot, but it's already a significant increase. So, you know, the run-up velocity and the run-down velocity, they are squared in the computation of the shear stress. So it means that if you increase the run-up velocity, it becomes rapidly unstable. So in this case, you see that I brought it to 6 meters per second. And look, it's unstable, and I need to bring the size of the units in order to stabilize it to something like 130, maybe, not yet, 140, still 150, it's still unstable, 160, unstable, 170, still unstable, 180. So what is here the conclusion? The conclusion is that I brought the run-up velocity from 4 to 6, and in reaction to that, I have to bring the size of the units from 100 to 180 centimeters, almost double. So you see that indeed the run-up velocity matters a lot. So let's go back to the original run-up velocity and the original size of the units. Let's see at the slope of the groin. So if I bring the slope to 45 degrees, happens is that, or let's put it to 40 degrees, sorry, or 38, because you cannot put the side slope greater than the friction factor, the friction angle. So in this case, if I bring to 30 to 38, but even if I bring it to 35, you see that it remains stable for the run-up. And of course, because if I incline more the side, with respect to the run-up, it becomes more stable, but then it gets unstable for the run-down. So if I increase the slope from 30 to 35, it's already, it's already a big change. So a simple application of the Schiltz criteria, which is physically based and it takes into account everything, everything but hiding, but the shape of the units, of course, but it takes into account most of the driving processes. Then you see that the simple application allows you to play with the numbers and to see what are the orders of magnitude, what it matters. And please pay attention to this, because hadn't we do an exercise, you probably wouldn't get this perception. What really matters? Velocity matters a lot. The slope matters a lot. So in order to get this perception, it is indeed important that you gain experience. And the way of getting experience is to do these exercises. And this is an exercise that can be done easily in Excel, as you see. So why should we use R? It's not motivated. And this is another message that I want to convey to you. It is important that you learn to use several different tools. Excel, MATLAB, R. They have different advantages. They provide different benefits, and they have different limitations. And then once you know a lot of tools, you can select the most appropriate tool for the quickest for completing your job. And in this case, I think Excel is probably quicker than R, because it allows you to play with numbers in a more, probably in a more productive way. But this is, of course, something that is subjective. I just wanted to show to you that we are not obliged to use R because we learned it. We learned it, and this is very useful because it allows us to make a proper selection of tools. On the other hand, I have no hesitation in using Excel if it turns out to be quicker than R. And this is, again, another message that I really want to convey to you. We didn't finish our exercise because there is the Hudson formula now. So let me first compute the coefficient. Let me not use, sorry. Coefficient KD of Hudson formula. I need to compute it based on NCR because this exercise doesn't give to me KD, it gives to me NCR. So let's go back to the page and see what is, let me open it. I'm sorry, I think it's already open somewhere. Let me check. No, it's okay. Just 1 second. I think I closed it. Ah, no, it's here. Sorry. Stability of rock and concrete armor units. Let me go to the Hudson formula. Here. I need to take this relationship here and invert it. So how to invert it? First of all, I have to take the power of 3 of both members. So NCR to the power of 3. And then divide NCR to the power of 3 by 0.8. Divide it by cotan beta, and I get KD. Okay, let me go to the Excel file. So NCR to the power of 3 divided by 0.8 divided by cotan beta. So let's, instead of dividing by cotan, let's multiply by tan. Beta, it's the slope. Okay, let me, I need the slope, I modified it to 35, then I'll be back to 30, okay? Because otherwise it's, let me put it 30. Okay, and let me see if everything is correct. And here too, I think it is a bit too low. Maybe because, let me check the formula, there is something that I am missing, I think, or maybe not, let me just check. It's power of 3 divided by 0.8 divided by cotan beta, okay. And let me check here. Let me check here what is, okay. Ah, yeah, okay. So sorry, I have to divide it by, let me look at the formula. I have to divide it not by 0.8, but I have to divide it by 0.8 to the power of 3. So here I need to 0.8 to the power of 3. Now 9, okay, 9 is fine. The coefficient KD, the range of variation is between 2 and 10, more or less. So I think 9 is fine. And now I have to apply the Hudson formula. So parameter W of Hudson formula. So the Hudson formula, let's go back to it. It's here. So I have to take gamma R, which is the specific weight of the Harbour units. So let me try to apply it, equal to specific weight of the Harbour units. Let's take it in kilogram forces. We can do that. And then I go back to the formula because I don't remember it by memory. Let me see. Okay, the cube of H is 1.27 the significant wave height. So let me do like this, times 1.27 times the significant wave height, which is something around here. Where is? I think I probably significant. Okay, here it is, 2 meters, perfect. And then I can close it and compute the power of 3. And then I have to pass to the denominator. The denominator is KD divided by, let's open a parenthesis, KD times, I go back to the formula, I need to see it. There is the immersed, the relative immersed weight. So I have to make the difference 2500 minus 1024 divided by 1024. Okay, this is okay. Let me look at the formula. Very good. And then I have to multiply, divide by the tangent of beta. Okay, and I think should be completed. Let me see. Okay, I think there is some, it's a bit too low. Yeah. It's a bit too low because let's put it in Newton actually. So I think here times 9 81. Okay, this is in Newton. And now here I can put the weight of armor units. And the weight, let's suppose that it's a cubic shape, then we can compute the volume of the cube, which is 100 divided by, oops, sorry. This one divided by 100, and this is to be cubed. And then I need to multiply it by the specific weight and times 981. Okay, so in this case, you see that the weight of the armor units is higher than the parameter W. So this is okay. I mean, it's stable. And let me put here a condition. If this one is greater than this one, let's write stable, or otherwise unstable. Very good, it's stable. Let's copy the format here and put the same format here. Okay, good. So basically, also the Hudson formula confirms that the units are stable, which is okay. Now let's try to make a comparison, and let's try to look at a lower size, like 90 centimeters. You see it's still stable for both. Let's go to 85 centimeters. The Hudson formula says that it's unstable. Let's go to 80 centimeters. Still, only the Hudson formula says that it's unstable. And now if I pass to 75, they are both unstable. Okay, so you see the comparison between the two formulas. It's, I think it is interesting. You don't have to be surprised. Let me see why I don't see on the screen anymore. 1 second. See my screen? Let me check. Okay. Okay. Yeah, you can still see it. And so you don't have to be surprised that you get different results. This is quite normal. And it's normal because these are two relationships that are very, I mean, they are different. They rely on different assumptions. One is empirical, the other one is physically based. Of course, you have to be concerned if the order of magnitude would be completely different. But in this case, it's not. The order of magnitude is not completely different. So, I mean, I think this is indeed something that it's instructive because it's, I think it's a useful exercise. Okay, now you have the Excel file available for download, and I invite you to play with it and to try to digest what I did in order to create this Excel file. Now let me share the screen because we are approaching the end of this lecture. And so I want to check if you have any question for me. Let me look at the chat. I also can stop the recording.